Hello, welcome to my presentation for the topic of how a Saxon bow is used for timing purposes. First, we're first we're going to talk about what is a Saxon bow. A Saxon bow is a bow with a hole in its base that sinks when placed in water. The Saxons use this device for timing purposes, investigate the parameters that determine the time of sinking. That's our goal. Okay, for the topic, I found a literature on the internet, but it had no theoretical explanation and it only adjusted one parameter. So I decided to conduct a research on my own, and that's what we're going to see now. Okay, my experiment setup is consists of coins, a polypropylene vessel, a stopwatch, a ruler, and also soldering iron and a bigger vessel. This is the experiment. For the experiment method, I had 9 values for 2 variables, which were the diameter and mass. For each diameter or mass, experiments were conducted to evaluate the average submersion time, and for each hole, 3 diameters were measured to evaluate the average diameter. And the average parameters and the errors were found by these equations that you can see here. For the equation development, these are my vessel parameters where x and h are variables. My assumptions are that there is no turbulence, a small sinking vessel thickness, and a small vessel section area ratio, and also the effect of viscosity on water flow is ignored, and also the water surface tension is ignored. And since the density of the polypropylene is nearly as water, the buoyancy force of the vessel material itself cancels its weight. Also, for the ignoring of viscosity effect on water, I use the dimensional analysis, which shows that the water viscosity in the vessel is relatively small in respect to other parameters of the vessel, so its influence can be ignored. So, for my equation developments, I modeled the system as a bigger pipe connected to a smaller pipe, which will be the bigger vessel and the sinking vessel. So I wrote the Bernoulli's equation and the equation of continuity, which I'll get the final equation of the derivative of x. And for the forces on the vessel, I have weight, I have buoyancy force, I have drag, and the change in momentum flow for the water stream entering the vessel. And also for the weight of coins, I had to calculate the effective weight of coins because of its buoyancy force, and also I had to calculate the buoyancy force of the vessel. For the calculation of drag, I use this equation, and for the coefficient of drag, it's related to the Reynolds number, which I calculated it by my average data numbers, data values. And also to calculate it, I use this graph, which shows the drag coefficient as a function of Reynolds number. And it gave me approximately the drag coefficient close to 1. And for and also the Newton's second law says the change in momentum flow entering a system will exert a force on the system. So I wrote the equations and got my force. And this is the Newton's second law summarized. And these are my 2 final equations that can be solved analytically. So I have 2 solutions. The first solution is that the h and x parameters change slowly and the system is in equilibrium state. So my equations will be simplified and I'll have 2 parameters that will be derived. And so now I can calculate the submersion time, and with some approximation, I can say that it's related to the inverse square root of coin's mass and inverse hole area. And these are the graphs showing the data and the function. And this is showing the time of submersion as a function of inverse square root of coin's mass, and also the time of submersion as a function of inverse hole area. And my second solution is by using Python programming language to solve the equations and using the tracker to track the motion. And this shows the solution by the computer and the track motion. And also these are the comparison of the both solutions, the computer results and the approximations for both function as submersion time as a function of coin's mass and whole area. And my conclusion We agree that the experiment and modeling results differ but have a close trend. Both solutions are close, but the second solution is slightly more compatible with data, and these are because of the ignored effects and approximated parameters. And these are my future goals with investigating the effects of vessel shape, investigating the effect of viscosity, investigating the effect of turbulence, and investigating the motion of the vessel in horizontal direction. And these are my references. Thank you for watching.